Jai Hind everyone. I Neeraj Sharma, Assistant Professor EC Department at Ajay Kumar Garg Engineering College, Ghaziabad. I am before you to present the video lecture for the series of complex topics for the subject which we are teaching for the current semester as per the AKTU scheme. So, in this semester, I am teaching final year students, final classes for the and where I have taken the subject microwave and radar engineering. So, this is the subject which I am, and it is a departmental elective subject whose code is KEC 074. So, for this subject, for this series of complex topics, I have chosen the complex topic, that is the MTI radar. So, what it will, its full form, and what is its significance, we will discuss later on. So, before coming on to our actual topics, just to go for a little bit regarding what we have discussed in the radar in our previous lecture. So, in my previous lecture which I have shared with you, so in where I have taken the topic radar range equation. So, where we have in that lecture I have discussed generally the basics of radar, what is its basic principle, okay, and how it will work, and after the working for the radar system, then the distance that is covered or the target which is available at a certain distance from the transmitter section, so that we have calculated, which we were named it as a radar range equation. So, in this continuation, so where what we did, so where I have discussed that the signal which has been transmitted from any transmitting antenna, then it will travel into a free space after let's say it have the covered distance r, and it will strike onto any target or object, and the target and object will absorb these EM waves which is reflected or which is transmitted from the transmitting antenna, and after that now these reflected back to the receiver section. So, at the receiver end, this radar section antenna will act as a receiving antenna. So, it will absorb the reflected signals, and on the basis of analysis of this signal, it will signify that they are the some distance, there any object or target which is available at a certain distance r. So, where we are interested with to calculate the value of the distance r. So, where we have also discussed the radar range equations as well. Okay. So, in this radar range equation, we have to derive, and we will able to identify the distance and able to calculate the distance which is traveled by the signal from transmitter to the target, means just be able to identify the location of the target, where at how much distance the target is available from the radar section. So, that we have discussed, and also in that we have also discussed regarding what the distance, how this radar range equation will affect or it will depend on to the different parameters like power transmitted, okay, and as well as the frequency. So, which have also some constant regarding that the frequency we can increase up to only a certain level, not more than radar cross section also, as well as the minimum detectable signal power that we have discussed. Okay. So, after that now we will that the summary I have discussed with you in detail about these factors, their mathematical expression we have also discussed. Now, again into the practical implementation of this radar methodology that we have discussed. So, for that point of view, radar methodology is now using. So, for practical implementation, number of many radars is now going to introduce, and that are using right now. So, in the continuation of this practical implementation, now today I am discussing with this topic MTI radar. So, this is my today's complex topic that I am discussing with you. So, what is this MTI radar and how it will work, and what the phenomena it is using, let me discuss. So, for that point of view, just I am moving with this MTI radar. So, first before moving on to the radar, in the continuation in this lecture, First, what is this radar? That is simply a radio detection and ranging. It's a name which it suggests, that means detecting the object and also identify or able to detect its range, means how much distance the object is available or target is available from the transmitting antenna or the transmitter section. Next one, that now we will move to this MTI radar. So for this MTI radar, so I am discussing here, this MTI radar is nothing but its full form is moving target indicator radar. Okay, so that is its name suggests, moving target indicator radar, and is its purpose of moving target indication is to reject the signal from the fixed or slow moving unwanted targets such as buildings, hills, trees, sea and rains, etc., and return for the detection or display signal from the moving target such as aircraft. So this is the now. So from this para that I have written here, so from the 2 points are coming here, that is which is focused, that is first one, that is fixed target, and second one, that is moving target. So these two types of object with us now, which can be available. So for our analysis point of view, this fixed target and the moving target. So for one by one we will discuss. So I think as per the discussion, there is no issue with the fixed target. That means signal can be transmitted from the radar and it is now reaching to the some object and it is reflected back. If it is fixed like if it is fixed like a tree or any rocks or any mountains, hills, buildings, etc., so that are not moving or not changing their position, so this can be easily detected with this fixed radar. So it is named as a fixed target, and it is no issue with the location of such type of target. But it is not an ideal situation. In ideal situation, right now the technology is advancing. So for that point of view, what will be the issue? That is means if subject or the target is moving from their position. So maybe sometime it will be on this position, here, up and down, whatever can be the position. So in that instance, our radar problems will be for the fulfillment of radar purpose to detect the signal or detect the target, it will become difficult in such. So for such type of cases, just let's say we are considering it as an aircraft. So that means they are not fixed, they are changing their position. Such type of targets comes under the category of this moving target. So here now there will be a challenge how we can detect its actual position, means the radar can able to identify the target is available at certain position and certain coordinates. So for that point of view, we are interested with the another application of radar that we are dealing here, that is the MTI radar, moving target indicator radar, that is specifically focused on to the moving targets only. They can able to detect the position of moving targets only, not the others. Okay, so for that point of view, we are using this moving target, and after identify the positions of this moving target, we can use the we can able to identify the distance or the position of the target where it is available. Okay, so for that point of view, we are using this MTI radar. So how it will work? Next question is that, means if we are certain frequency we are transmitting, and for the certain frequency we are getting the reception. So we are for fixed that, but in the MTI radar, how we can fulfill this requirement? So for that point of view, it will MTI radar for to detection of the moving target. What we are doing, we are using the Doppler shift imparted on the reflected signal by a moving target to distinguish moving target from the fixed target. That means from a fixed target, we are differentiating for the moving target with the help of this phenomena, Doppler shift, and corresponding to this Doppler shift, the frequency will named as an Doppler frequency. So first, before moving to this MTI radar, we will first discuss with the Doppler shift. What is it? So here I have discussed regarding this Doppler shift. What is it? When the radar waves are sent towards a moving target or object, they are reflected band and received by the receiver. If the frequency of the reflected wave is increased, it means target is moving toward the radar, and if the frequency is decreased, that means the target is moving away from the radar. So this is the concept. That means what we are discussing with the change of frequency. That means here we are discussed with the relative frequency. We are discussing with the relative motion of the target, and we are studying for that. If we will able to the discussed or identify the corresponding relative phase shift, then we can able to identify its actual moving target position. So what will happen in this? So for that point of view, just let me explain. Let's say any transmitting antenna which has been transmitted a signal like this one, okay, and let's say here any target is let's say it is an a target, okay. So it's an a what? Just a minute. It's a moving target, and let's say transmitted signal has been transmitted with frequency f0, and there will be a certain reflection for this transmitted frequency f0 according to the relative phase shift or the relative frequency. What will happen? The moving target will revert back the reflected frequency like f0 plus minus fd, okay, f0 plus minus of this fd. So actually the signal which is transmitted having the frequency f0, but for this f0 it is reflecting back the another frequency of f0. Let's say we are considering that is the f0 plus minus of fd. So here from the analysis point of view, our actual position as per the our actual frequency f0, we have the corresponding phase shift, frequency shift we will observe, frequency discrimination we will observe, that is the fd. This fd is nothing but the Doppler frequency. It will give the significance of the Doppler frequency. So to calculate this Doppler frequency fd, we have to calculate this value of fd. So it will give the about the position of the, that means it will, if this frequency is increasing, that I have already discussed here, if the reflected wave is increased, it means target is moving toward the radar. If it is decreased, that it is going back to the or moving away from the radar. Okay, so this is the simple Doppler frequency shift concept. So for that point of view, if we have to calculate this value of fd, let's say omega d is equal to 2 pi fd, that is simply omega d is equal to d phi by dt, and phase is what? Total phase we will calculate 2 pi into part difference. Part difference is what? 2r by lambda from transmitting to target and target to receiver. So the distance it is traveling from here this antenna to this, that is the r, and reflected back towards, so total distance covered is 2r. So total phase shift will become 4 pi r by lambda, and after that we will put the value in this equation. Okay, so when we will put this value d by dt, when we will put d by dt 4 pi r by lambda, and after the solving we will get the value of fd is equal to 2vr by 2vr upon lambda value. Fd is equal to 2vr by lambda. That will give the value of this Doppler frequency. So we will corresponding to the our actually transmitted frequency, we will also focus or analyze this Doppler frequency shift Doppler frequency shift change we will also observe, and on that basis we will able to explain that our target which we want to detect, that is fixed or moving. So we will change if we will observe this FD, then what we will say, the target is now moving. Okay, so that concept is now using into this MTI radar. So this will be the picture that you are looking here. That will be our block MTI radar block diagram that you can see here. So for that point of view, here we are using as a power amplifier. We can also use a power oscillator in this, but here we are using that power amplifier. So in this block diagram, as you can see, this power amplifier is connected with the pulse modulator turn end of our transmitter section, and on this power amplifier we have providing the output from this mixer 1 and mixer 2 we are also using here, and we are the component which we are using, that is local oscillator. Local oscillator is also named as STALO, that is the stable local oscillator. Let's say it will have a frequency, this section will have frequency Fi, let's say we have defining it, and the coherent oscillator will have the frequency. This coherent oscillator will have the frequency corresponding to, let's say we are now detailing it or name it as an FC. Sorry. FC. Okay. So let's say these two frequency we are now using here. This is simple local oscillator frequency, and this is our coherent oscillator frequency, from where we will generate the reference signal. Okay, on that basis we will able to define or identify the position of the moving target. Okay, and also we are using here the duplexer and IF amplifier as well as the phase detector. So this will be the and also we are phase detector output we are providing to the delay line canceller, and after to study the delay line canceller output, we will able to or we can able to get the position of this moving target. So how it will work, we will see one by one. So here let's say the frequency which is transmitted from this local oscillator Fi and coherent oscillator generating the frequency Fc. So mixer 1 will get here we are also transmitting Fc, we are transmitting here Fi, also here Fi, and here also Fc we are transmitting. So from mixer 1 it will generate the frequency Fi plus Fc. Okay, what? Because this mixer will perform the mixing operation. Mixer generally it is also an electronic device, will perform the mixing operation, in which if we are transmitting, if there are two input are applying onto the mixer, let's say F1 and F2, and so after the mixing performance it will generate the output MF1 plus minus NF2. So here we are getting this mixer 1 will provide the output Fi plus Fc. That means it will act as an adder circuit. This mixer will perform the summing operation, adder or summing operation we are performing here. Okay, now after that this output is now provided to the power amplifier when it is turned on. So let's say we are giving the output is coming here Fi plus Fc. Then this Fi plus Fc output has been provided to the duplexer. So duplexer is also another electronic device. So it will also give the simplicity or the reduction in size for the electronic component, like in spite of we are using the two antennas like transmitting or receiving antenna, we are using only a single antenna. So at a transmitting end it will act as a transmitting antenna, or for the receiving mode it will act as a receiving antenna. Okay, so this will be the working of this duplexer. So in spite of using two, we are using only one antenna. Now next what will happen? After that, this duplexer, it will transmit this frequency Fi plus Fc into the free space from this antenna, which is acting as a transmitting antenna. After the transmission, at a certain interval, their sunny frequency will be received by this duplexer, where this antenna will act as a receiving antenna. So it will, let's say, receive the frequency, let's say it is Fi plus Fc, corresponding to the what we have actually transmitted. So we have transmitted this Fi plus Fc, and for that we are getting the frequency Fi plus Fc plus minus of Fd. That, let's say, this we will now get onto the receiving antenna at the duplexer section. So after that, in spite of what we have transmitted, where local oscillator frequency Fi and our reference signal Fc frequency, that we have summing of these two we have transmitted. So for that we are receiving this receiving frequency Fi plus Fi Fc plus minus of Fd. We were receiving this frequency. So this Fd, what we have received, that is the Doppler frequency. So for that we have already discussed in our previous slide. I have discussed already. So because we have to analyze its actual value, or analyze this Fd to get the position of the object, it is stationary or moving. So the frequency which we have received, that is Fi plus Fg plus minus Fd. Again now we are applying this input to the another section of this mixer 2. This mixer 2 will again also perform the mixing operation. So here this mixer 1 we have used as a summing circuit. So here this mixer will are getting the two input Fi Fc plus minus Fd, and as well as it will getting the frequency from the local oscillator, it will be Fi. So what we are using, so here the output of this mixer 2, that is the Fc plus minus of Fd. Okay, Fc plus minus of Fd. That means we are subtracting the this local oscillator frequency. That means this mixer 2 will perform the subtraction operation. This will perform the subtraction operation in this. Clear? Now after that, so this local oscillator frequency we have now, for the stable local oscillator frequency it is eliminated. So this output is now applied to this IF amplifier stage. So after this amplifier stage, we will get this output applying onto this. So what we are receiving here, so after that it will perform this IF amplifier is also a part of super heterodyne operation will perform here. So after the super heterodyne operation, which will produce the IF signal, and this IF signal will now applied onto this phase detector. So again now signal will move on to this phase detector. So after the phase detector, it will have the two frequencies, some frequency Fc plus minus Fd which is coming, and for that, and it will have the another reference signal, that here we are also providing the reference signal. So after this reference signal, it will verify this intermediate frequency which is observed from the super heterodyne operation, and it will applied onto the delay line canceller. Now this output, after that we will study, because we are aware this Fc frequency, and on the Fc we will, after this Fc we will also focus onto this Fd, which we will get from the receiver section, and this will be applied to the delay line canceller. After this delay line canceller, we will give it to the our oscillo display, where we will observe the output. So for that point of view, before moving ahead, we have to go for the delay line canceller first. So here this delay line canceller that I have used here, it will is actual diagram. So as you can see here, the trans antenna which is connected to the receiver section, that we have provided the detailed delay line. So output that we are getting, that is the bipolar, and after that bipolar is now applied onto this delay line, whose time duration is 1 upon the pulse repetition frequency or pulse repetition interval is time equal to. Okay, then we are applying to the subtractor input, these two input, delayed or undelayed we are applying input, and after that we are giving to the full wave rectifier, and now we are getting the our unipolar video to the indicator we will see. So in this delay line canceller also of the two type, time domain filter oblique canceller or the frequency domain filter or canceller we can use. So here the delay line canceller is used to the separate the Doppler shift echo signal moving target from the unwanted echoes. So that means first of all we are performing this operation for the with respect to the stationary, and the output obtained after the subtraction of these two successive sweep is bipolar, and it is converted to unipolar by the means of full wave rectifier. And the unipolar video is needed if an analog display is used that require position signal, and the digital signal now converted to an analog by digital to analog converter, and we will see it onto the PPI plan position indicator display. So this is simply a delay line performance that we are using here. So first of all, how we will provide this delay line. So for that, what we are using, in spite of electromagnetic transmission line delay, we cannot provide directly, and it give not the exact value. So first of all, we will convert this electromagnetic signal to acoustic signal, and on that acoustic signal we will apply the delay, and then this delay will provide converted back to our actual EM signal. So this is the working process in this delay line. So after this delay line, now what we are getting, so here before getting to the reaching to the output, just you can I have also mentioned the component, that is what I have used here, power amplifier. Like here I can use the 2 cavity klystron, TWT, you can use pulse modulator, duplexer, mixer, stable local oscillator, coherent oscillator, IF amplifier, phase detector, delay line canceller, that all the component which are I have mentioned here, that can be which I have used, that can be also listed here. So after that, now we will moving toward the MTI radar display. So this MTI radar display, how we can able to identify the target that is fixed or moving. So for that point of view, we are using this curve. So here A to E, A, B, C, D, E, F, two signal plots you can looking onto the display. So here you can see that in the A slide, in this in figure A, you can see that this target will gives the position, this change variation in amplitude will give the information regarding the fixed target, and the position which is showing by the two arrows, this one and this one, this is for the moving target. Let's say we are now, this sweep we are now considering for the in figure A. From B to E, from this to this, we are now using here the another sweeps corresponding sweeps we are using here. So we can observe that from all these MTI radars at the display, for this MTI radar, we are finding that with reference to the A figure A, what the target, the position or amplitude for this fixed target is not changing through all. So that is the F is our resultant sweep at final display, where we are able to identify this is fixed or moving. So which is now displaying in this figure F. So here you can see that from B to E corresponding to A, target amplitude is not changing. So after subtraction, you will get this same output. So this will be the regarding in the information for the fixed target. But with reference to this A, from B to E, you can see that amplitude position here for this, it will decreasing, again decreasing, and also decrease. So for the same also, so we are changing, we are realizing that our this signal position is now, amplitude level is now decreasing. Okay, in all the sweeps from B to E respective, we are comparing with this figure A. So from that point of view, at the final sweep, in where we are locating this one observation from the delay line canceller, on the basis of we are giving the confirmation regarding the target is moving or fixed. So this highlighted or amplitude corresponding to sweep A, which is signifying from figure A, for the rest of B to E, that it will give the information that this clutters type of echoes we are getting onto the radar display. So it will give the position for the moving target or the information regarding the moving target, which is specifically based onto the internally onto the concept of this Doppler frequency. So this two curve, this one and this one, will signifying that the target is moving. So in this way, this moving target indicator radar will work. So after that, this is the simple working of this MTI radar. And also there is one issue that comes with this MTI radar, that is the blind speed. So this is also we have to taken into the consideration. That means if radar is our moving uniform velocity, moving with the uniform velocity, and the respective phase shift is not if it is 2 pi, but for that we are getting some wrong information. So corresponding speed will named as an blind speed. This issue may come into the MTI radar section. So this is the MTI radars output that I have already discussed, and this regarding this MTI delay line canceller, how this delay line operation perform from B to E with reference to A is now mentioned here from this diagram that I have discussed here. So this is the now from my side for this MTI radar, the references which I have considered, that is I have referred the book Skolnick, which introduction to radar system, that I have taken it as a reference for the explaining the concept of this MTI radar. So thank you. Jai Hind.